All right, we're going to do 6-6, which is the Pythagorean theorem. And 6-6 starts on page 256 in print and page 256A in Braille. We're in volume 24 in Braille. It's on 256A. There's a little bit of information on 256A about trying to show some history of a stamp that commemorated the 2500th anniversary of the Pythagorean theorem. The tactile's not very good. So we're going to turn the page to the next page, 256B, and start from there because that tactile is much better. So if you could get yourself to 256B in Braille, and 256 in print, in the midst of the page there's a graphic with 3 squares that are gridded that come together to make a triangle in the middle. So Braille and print users, we have this graphic, this tactile. If you'll notice, it is 3 gridded squares, and to the furthest left of our tactile is a square that is gridded into 9 little squares. It's a 9 square unit square. It's a 3 by 3 square. If you remember from your area days back in pre-algebra, probably find out area of a square by doing side by side. So this would be 3 units by 3 units. If you count all the little units, we have 9 units. 3 times 3 is 9. The square immediately to the bottom increases by 1 unit on each side. So it's a 4 by 4. Slight little interruption there with announcements. Now we're back. So immediately to the bottom of this drawing, you have a 4 by 4 square that you should be able to make out. It's 4 units across by 4 units down. And so a 4 by 4 square would mean there would be 16 units in this little square, correct? And then up to the top right at an angle, there's a square that now increases by another unit in each direction. And it's a 5 by 5 square. So it would be 25 total units in that square. And this drawing is having those squares come together at their corners to create a triangle in the middle. And notice that the square on the left and the square to the bottom come together at a perpendicular angle. So there's a little right angle indicator in the bottom left corner where they come together. So that says, aha, I have a right triangle. And directly across from that right angle indicator would be my hypotenuse. So the left leg of my triangle would be 3 units. The bottom leg of my right triangle would be 4 units. And my hypotenuse would be 5 units. And if we have these squares coming together, a 25 unit square, the square root of 25 is 5. That's our hypotenuse. A 9 unit square would be the square root of 9, which is 3. That's one of our legs. And a 16 unit square would be the square root of 16 would be a 4 unit for one of our legs. If we add the 9 units of our leg together and the 16 units of our bottom leg square together, we get 25, which is the same number of units as the side of the hypotenuse that's been created by the square. So what this is showing in a graphic form is that 25 equals 9 plus 16, or 5 squared equals 3 squared plus 4 squared. It's showing and proving the Pythagorean theorem. So on the next Braille page, or actually 2 more Braille pages over, there is the Pythagorean theorem, Theorem 6-9, and down at the bottom of page 256 in our blue box. So this is on 256D. In words, up at the top, it says Theorem 6-9, Pythagorean Theorem. In a right triangle, the square of the length of a hypotenuse, C, is equal to the sum of the squares of the lengths of the legs A and B. So it just shows a right triangle, and it details the legs A and B. Those are the two sides that come together at a right angle. Those are your legs. You know those from learning definitions of right triangles. And the angle directly across from your 90-degree angle is your hypotenuse. And in the Pythagorean theorem, we call one leg A, another leg B, and the hypotenuse is C. This is a review of a theorem you've done in pre-algebra and algebra, and it's the Pythagorean theorem, and you've learned it as a squared plus b squared equals c squared. They write it just in reverse. In symbols on the bottom underneath your drawing, it says c squared equals a squared plus b squared. Doesn't matter, does it? We can write it in any order. A squared plus b squared equals c squared, or c squared equals a squared plus b squared. So if we turn the page, it gives an example on how to use it. If you know the two measures of the sides of any right triangle, you can find the third side by using this theorem. It uses some basic algebra. So the first example says, find the length of the hypotenuse of the right triangle. So they have a graphic of a right triangle with a leg on the left-hand side extending from 12 o'clock to 6 o'clock, a leg at the base extending from a 9 o'clock position to 3 o'clock position. Where those two legs come together is a right angle indicator. So you go, okay, good. I've got a 90-degree angle, so directly across from that 90-degree angle, I have the hypotenuse. The leg on the left, they're identifying that as 15 feet. Your leg at the bottom, they're saying is 8 feet. And the hypotenuse, they're saying is c feet. So we have to find the hypotenuse. So if you turn the page, it walks through the steps and the theorem, the proof to finding the hypotenuse. In print, it's directly on this page at 257. In Braille, we're on 257A. So it starts with c squared equals a squared plus b squared. And the reason why we can write that is because of the Pythagorean theorem. The next line says c squared equals 15 squared plus 8 squared. And the reason why we can do that, it says, is we're replacing a with 15 and b with 8. And what I'd like you to write further is that you're using the substitution property to do that. You can substitute the values in for a and b. Then in the next step, it says c squared equals 225 plus 64. And that's where they've used rules of exponents, where 15 squared equals 225 and 8 squared equals 64. And they detail that. And you could go further and say, I'm able to do that because of rules of exponents or exponent rules. Then it says c squared equals 289 because we simplified it. We added the 225 and 64. Then finally it says c equals the square root of 289. And the square root of 289 is approximately, or not approximately, it is 17. So we take the square root of both sides because we want to get c by itself. It was c squared, and to undo squaring, we have to do square rooting. So we use the square root property of equality, and c equals 17. So the length of the hypotenuse is 17 feet. So there's the proof. We added a few more words. I want you to think like that, kind of be geometry attorneys, and ask yourself, why can I do each one of these steps? And that gets us the hypotenuse. Now turn the Braille page to 257B, and in print we're looking at the next example, example 2. And find example 2 on your Braille page. It's a few lines down. It says, find the length of one leg of a right triangle if the length of the hypotenuse is 14 meters and the length of the other leg is 6 meters. And it gives a drawing, has a right triangle, the leg on the left that they're labeling 6 meters. It is perpendicular to the leg at the base. There's a right angle indicator at the bottom left vertex. And then we have a hypotenuse directly across from that, and that is labeled 14 meters. So we have to find the missing leg. So we can use the Pythagorean theorem and some basic algebra and find that. So Braille users turn the page, and there's the proof, the steps for doing that. Print users look directly below the drawing. So we start out with c squared equals a squared plus b squared, and the reason why we can write that is the Pythagorean theorem. Then we write 14 squared equals 6 squared plus b squared, and the reason we can do that is because of substitution. We're going to replace the c with 14 because that's what we were given in words and on our drawing, and we're going to replace the a with 6 because we were given one of the legs. We're left with just the b squared because we don't know that yet. We're going to solve for b. So in the next step, 196 equals 36 plus b squared, and that's because of exponent rules. 14 to the second power is 196. 6 to the second power is 36. Then the next step shows subtraction of 36 from both sides. 196 minus 36 equals 36 plus b squared minus 36. And that's because we need to get b squared by itself, and 36 is hanging out next to it, adding itself to it. So to undo a positive 36, we need to subtract 36 by using the subtraction property of equality. Then it simplifies. 196 minus 36 is 160, and we're left with b squared on the right because 36 minus 36 is 0, and 0 plus b squared would be b squared. So we have 160 equals b squared. That's just by simplifying. Then we have to do the square root of 160 because in order to get b squared by itself, you have to square root it to get b by itself. So you square root both sides. That's the square root property of equality. This is an imperfect square, so it shows that you could plug it into your calculator. Some calculators use a second function square root key. Your Braille note, you could put your square root and the number in and enter. And you will get the answer 12.64911,064. It didn't tell us what to round it to, so by rule of thumb, at least round it to the tenths. So the answer would be approximately 12.6 meters. So this is showing how you can be given a leg and a hypotenuse and find the other leg. When you do that, you have to do some subtraction. You have to subtract the square of the leg from the hypotenuse and then square root it. So on the next page, it shows a couple of drawings, and it says your turn. We would have to find the missing side on each one of these triangles. So a little letter A has a triangle that has a leg on the left that is 6 meters, a leg to the base that is 8 meters, and a hypotenuse that is c meters. There's a right angle indicator at the bottom left vertex. So we know this is a right triangle. We have a leg, and we're missing the hypotenuse. The Pythagorean theorem can be used to find the hypotenuse by doing substitution for a squared plus b squared equals c squared and doing the math. Little letter B, you have a triangle, a right triangle that's kind of sitting in a different position. There's a leg up top going immediately to the right to the leg on the right. There's a right angle indicator at the top right vertex, and then your hypotenuse is directly across from that right angle. The leg at the top is 12 feet. The leg to the right is b feet, and the hypotenuse is 13 feet. So you're missing a leg, you're missing your b value. You still use a squared plus b squared equals c squared, except you're going to substitute in 12 for a. You're going to keep b. You're going to substitute in 13 for c. And you're going to do the math. and come up with the leg that is missing. If you turn the page in Braille and look immediately at the bottom of the page in print, there's some directions that says if C is the measure of the hypotenuse, so you're being given some information, find each missing measure and round to the nearest tenth if necessary. So little letter C gives us A equals 7, B equals an omission, a question mark, and C equals 25. So we plug this information in to find our missing leg B. A squared plus B squared equals C squared. Little letter D has A is missing, it's an omission, B is 10, and C is 20. So again, A squared plus B squared equals C squared. We don't know A, but we can plug in the value of B, which is 10, so 10 squared. A squared plus 10 squared equals the value of C, 20, so 20 squared. Simplify, or do your exponents. Use your subtraction property of equality, simplify, and square root to get the answer. The next, there's a page break for 258, and turn the page print users. This talks about kind of a real life problem using right triangles and the Pythagorean theorem, and it's used in construction. And number 3, example number 3 says, in pitched roof construction, carpenters build the roof with rafters, one piece at a time. The rise, the run, and the rafter form a right triangle. The rise and the run are the legs, and the rafter is the hypotenuse. Find the rafter length for the roof shown at the right and round to the nearest tenth. So that should sound familiar. If you hear rise and run, what does that sound like? Slope, isn't it? And that's what the rafter is this line that's at a slope. But now what we're doing is we're taking the distance of our rise and the distance of our run, and we're using the Pythagorean theorem to find the distance of our rafter, or the hypotenuse. And the drawing on the next Braille page, the drawing immediately below all that writing in print, shows kind of that detail. The rafters, it tells you that this is the rafter length on the left. It's at an angle. And then there's a rise going up and down from that top vertex and a run going left to right. It's saying the rise is 6 feet and the run is 12 feet. So our legs are 6 feet and 12 feet. So if we do 6 squared plus 12 squared equals C squared, we can figure out what our rafter length is. And again, they start doing that by detailing out what you know, and then coming up with a plan and then solving it. On the next page, it goes through the proof of the solution. It's just the same as the last proofs. You use the Pythagorean theorem, you use substitution, you use your exponent rules, you simplify, and then you square root both sides, and you round to the nearest tenth to get the approximate value of your hypotenuse. All right? So that's how to use it in kind of real life story problems. Now, the next bit of information has us explore and remember that we could use the converse of the Pythagorean theorem to tell whether a triangle is a right triangle. So maybe you're given 3 sides, 3 measurements of a triangle, and you want to determine if it's possible for it to be a right triangle or not. You could plug those 3 sides into your Pythagorean theorem, and if they equal, if one side equals the other, a squared plus b squared equals c squared, then you know it can be a right triangle. If they don't equal, then it's not a right triangle. And that's what Theorem 6-10 states. And this is on page 258C, Theorem 6-10, and at the very bottom of your page of 258. It says, if C is the measure of the longest side of the triangle, and that's what our hypotenuse is on our right triangle, the longest side, A and B are the lengths of the other 2 sides, and C squared equals A squared plus B squared, then the triangle is a right triangle. So we can do the converse of our Pythagorean theorem to prove whether a triangle is a right triangle or not. So in example 4, there's a page break on this Braille page for 259. Print users, look at 259 example 4. There's no drawing. It just says number 4, the lengths of 3 sides of a triangle are 5, 7, and 9. Determine whether the triangle is a right triangle. So, since the longest side is 9, we're going to use that for our C value. That's our potential hypotenuse. The other 2 values are our legs, and it doesn't matter whether we use one for A and the other for B. They're interchangeable because they're adding to each other, and addition is commutative. We can add A plus B, and it's the same as adding B plus A. So we prove it on the next page in Braille and in our example underneath the words there. So C squared equals A squared plus B squared because of the Pythagorean theorem. We use substitution and we replace C squared and we say, does that equal, a little question mark over, does that equal 5 squared plus 7 squared? And we replace the values of C using C, A, and B using substitution. Then we do some simplification. We do our exponent rules. 9 squared is 81, 5 squared is 25, and 7 squared is 49. So we have 81, does that equal 25 plus 49? We simplify some more by adding. 25 plus 49 is 74. 81 does not equal, a slash and equal sign does not equal 81. So therefore, this cannot be a right triangle because we can't use the Pythagorean theorem. It's just a scalene triangle. We don't know what the angles are. So in your turn, it gives you the opportunity to try it again with 3 sides. So little letter E all the way at the bottom of the page gives us 3 sides, 20, 21, and 28. So we go, okay, 28 is our longest side, so that would be our C squared. 28 squared has to equal 21 squared plus 20 squared. So if we do that, we go 28 squared.
2, 8 times 2, 8 equals 784.
Got 784 has to equal 20 squared plus 21 squared.
2, 0 times 2, 0 equals 400. 2, 1 times 2, 1 equals 441.
So we have 441
plus 400 equals 841.
That does not equal 28 times 28, does it?
2, 8 times 2, 8 equals 784.
So this is a no. Those 3 sides can come together and make a scalene triangle, but they do not make a right triangle. In little letter F, we have 10, 24, and 26. So 26 is the longest side. It's the potential to be the hypotenuse. So we square it.
2, 6 times 2, 6 equals 676.
So we want to try to see if we can equal 676 with the 2 legs added together after we square them. So 10 and 24. So 10 squared is 100. What is 24 squared?
2, 4 times 2, 4 equals 576.
We add the 100 to it, the 10 squared.
Plus 100 equals 676.
So sure enough, we get 676. So yes, 10, 24, and 26 can be put together to form a right triangle. So that's a way to use Pythagorean theorem to prove whether a triangle is right or not if you know all 3 sides. So now you can use it to find a missing side, and you can use it to prove whether 3 lengths could be a right triangle. So that's the end of 6-6. It's a big review of the Pythagorean theorem. For practice, you should do the check your understanding. It would be from like 1 to probably 30, actually 40, yeah, 1 through 40 would give you mass practice at it. At minimum, what you should do is do a couple of problems and write it out in proof format. Solve it, but then say, okay, why can I do each step? Just as it was done back in examples 1, 2, 3, and 4. They wrote out each step and wrote out the reason why you could do it. That's the kind of stuff you're going to need to do on the end of course exam, is write the proof also. So that's the end of 6-6. We'll see you in the next section.